All right, so hey everyone, gonna give this a shot. I wanted there to be some opportunity to put this lecture online for those of you who missed class today, but also for those of you who want to maybe give it another listen, because I know this is a kind of complicated idea and we're covering it very quickly, and there may be things that I glossed over a little bit or that maybe you missed. So I'm going to basically redo the lecture that I did in class today as closely as I can. I will say that there were a couple points in class where I sort of paused and said, hey, draw along with me. For the sake of brevity, I'm just going to kind of keep going. But I highly recommend, especially if you weren't there for the lecture today, that as I'm going along, you pause the video and draw along with me, because I think it'll really help it make a little more sense. So, as you can see in my chicken scratch, we're talking about linear perspective. And when we talk about a perspectival system, so again, we've already talked about atmospheric perspective, a perspectival system is essentially something that allows us to cue the viewer in to the relative placement of objects in a space. So atmospheric perspective uses the atmosphere, uses lightening and darkening of objects to let the viewer know how deep into the picture plane something is. The darker it is, the closer it is, the lighter it is, the further away it is. Linear perspective obviously uses lines to do that, and it's really designed to help us draw rectilinear forms. So rectangles, boxes, furniture, architecture, anything that can roughly fit inside of a rectangle or a box, linear perspective is very useful for. It's also very useful for drawing cylinders and ellipses, although we'll get to that next time in a separate lecture. I don't want this to be too long. So anyway, the history of linear perspective is not incredibly important, but just for some very brief context, I showed in class this Giotto, which I've marked up a little bit here. But essentially, Giotto predates what we call the rediscovery of linear perspective. We're pretty sure that other civilizations had linear perspective before the 1400s, but as far as we know, the information was lost. So we say that it was rediscovered in Italy in about 1440. So this is a Giotto painting that predates that, and it feels pretty good. So I outlined this bench here that kind of shows how there we go. How Giotto is separating out the sides of this bench so we can see the left side and the top and the front, which lets us know that our head is sort of positioned somewhere here. This is off to the lower right of us, and that the bottoms of these pillars, the floor, that we can see the right side of these pillars over here, the bottom of the ceiling. There's all this information cueing us in to sort of bring our head into this little spot that I've painted here into the painting, and letting us know kind of where we exist in the space. But you may feel that it still feels a little off, especially in this back room. The floor kind of feels like it tips up a little bit, and these figures off to the left kind of feel like they're floating in space. And it's just not quite perfect. And in the 1400s, when people like Brunelleschi were trying to come up with these schemas that would explain the way that things looked in space, they were trying to come up with something that was more foolproof, that was more mathematical, more scientifically focused, and they developed a series of visual laws that describe how things appear when they are in a continuous space. And that allowed them to do drawings like this, which is a much layered drawing. This is 1750s. This is by Paolo Uccello, who's another Italian, but very convincing representations of dimensional forms on a two-dimensional surface in a way that now almost looks like a computer model, but was actually done all by hand, and to an extent almost done mathematically, that all of this can be figured out and solved for and proven. And we're not going to go that deep into it. We don't need to know the mathematical proofs of things, and we don't even quite need to know how to draw something like this. But I want to talk about the basics of linear perspective and how it can be useful for making certain kinds of drawings. So let's begin with a box. So I'm going to be relatively quick and sloppy while I draw this because it's the general idea of things that counts. But I can go ahead and draw a box, and I just based on information that perhaps I'm looking at, I can get a sense of where I exist in relation to this object. So I can see the top. So I probably assume that my vision is, my head is somewhere above the box looking down because I can see the top of it. And as I move this box to the left or right, or up and down, I'm going to expose different amounts of different sides of this box. And so we understand that. But I might feel, for example, that these boxes don't quite look like they're in the same space. Or maybe I have an object that I want to sit on a table, and I can't quite get it to feel like it's sitting properly. Maybe it feels like it's floating a little bit, or the table is flipping up, or one of these common problems. And it might seem like, well, there must be a way to take that guesswork out of it, to make these rectangular objects feel like they're in the same space together. And that's really the goal of linear perspective, is to come up with some way that can explain how these objects exist in space together. And essentially, how linear perspective was derived is it was actually a slightly more complicated system involving a series of drawings with holes in them and mirrors that you can, maybe I'll link to a video about because it's kind of interesting. But for simplicity's sake, let's just imagine that these three boxes here actually exist in space. They're sitting in space. And I have placed a pane of glass in front of them, and I need to trace on top of them to show, I'm basically tracing what I'm actually looking at. I'm keeping my head fixed in space. I'm tracing on this pane of glass. And what these artists figured out is that if I trace all of these lines and I carried them back into space, doing this a little sloppily, but they would all appear to touch at a single point. All of these objects, even though they're all saying at different points of drawing, all of these diagonal lines converge at a certain point. And the reasoning for that forms the foundation of what linear perspective is. So we're going to talk about that a little bit. So let's start with the first thing, which is let's imagine a horizontal line spread across our image. This horizontal line here is going to represent the horizon. It's going to represent, if we were outside, the literal horizon, the point where the sky meets the earth. So let's begin by putting a box in this scene. What I would find is that if I begin sort of standing up above this box, I can see the top of it, and the horizon appears to be above that box. There's space between them. If I were to get down on my hands and knees and sort of squat on the ground, so that my eye was right along the ground, now the box sort of appears like it's sitting on the horizon. And so what we've discovered is that the horizon always follows our eye level, that the horizon represents where in a scene our eyeball is, what its height is from the ground. So for example, if I could put my eye exactly on the ground, the horizon would appear to sort of meet that. And if I could, stand up, and place a box on the ground, the horizon still stays kind of where my eye level is. So that's the first thing. Another thing that's going to be important is the idea that if I take an object, let's say I place it 10 feet away from me, if I take that same object and move it back into space, so let's say it's 20 feet away from me, it appears to get smaller. So, two simple laws, that the horizon is our eye level, and that objects appear to get smaller as they go back in space. Now, let's take something that goes back in space infinitely, or at least as far as we can see it. So let's take a pair of train tracks, for example. They're sort of extending off into the distance. Now, we know that in actuality, these train tracks are parallel. They run parallel to each other. These train tracks are never going to touch. But when we lay them out into the distance, and they go as far as we can see them, they do appear to touch. They appear to meet at a single point. So, something that is further away from us, something that gets further away from us, appears to get smaller. If it goes all the way to the point that we can't see it, it appears to meet at a point. And that point always sits at our eye level, because it always disappears where we can't see it anymore. So it disappears at the horizon, which is where our eye is in the scene. And so part of what the laws of linear perspective do is they take all of these rules together and they help us create a scene that feels contiguous. So let's start again with our horizon. And I'm going to start drawing a little rectangle here. Now, I can try and just sort of guess what the angle that creates the top of this box is going to be, but I know that if this box were infinitely long, it would meet at a point on the horizon. So what I can do instead, bear with me. What I can do instead is I can start with that point. Oh, this brush is not working. I should have tested this before I started, so I made sure I had something that would... Oh, we'll just use this. Sorry about that. So I can start from a point, connect that point to the corners of my box, and then run a horizontal along, and just sort of slice that infinitely long box off, and I have a pretty convincing box. And so this is somewhat useful, but where it gets really useful is, again, if you remember those train tracks, that parallel lines appear to me at a point. So any box that is parallel to this box, whose sides are parallel to this box, so any box that is, in a grid, so to speak, with this box, all of its angles are going to meet at that point too. And I can draw a box anywhere I want in space, and it will appear to recede correctly if I make all of these diagonal lines, which we are going to call orthogonals. If I make all these orthogonals recede to the same point, it will always appear to exist in the same space. And so I could, for example, if I start from the front, I could, for example, make a tabletop that my objects sit on erase some of these orthogonals that I no longer need. And now my objects appear to be sitting correctly on this tabletop because all of my diagonals are meeting at the correct point. All my angles are correct. Now, two more words of vocabulary before we move on. For the rest of this video, I'm going to be calling this line, our horizon, the horizon line. Even though it also represents our eye level, we tend to call it the horizon line. And we're going to call this point that things recede to the vanishing point, which is, again, the point where an infinitely long object would appear to disappear. So, this all seems very useful. And actually, I might recommend, at this point of the video, making a little test drawing. So let's draw a horizontal line and draw 9 boxes. So a box to the left and the right and centered on the vanishing point above and below. So I have 9 boxes. And connect all of these boxes to the vanishing point. Just as a quick little sample of all the kinds of ways we can move around space in linear perspective. So pause the video and do that real quick. I think it'll maybe help some of this make a little sense. So anyway, this may seem very useful, but you may also be wondering why, for example, we haven't been covering this from day one, if it is so useful. Why didn't we talk about it as the first time that we looked at a box? And there are a few reasons. The primary reason is that it doesn't apply to every situation. So for example, you've noticed that in the system that we've been using, everything recedes to a single point. We call that a one-point perspective system. But a one-point perspective system only works if that front face of the box you may have noticed, is made up out of perfect verticals and perfect horizontals. That's the only time that one-point perspective works. And that's only the case when the line of our vision is perfectly 90 degrees from the face of the object. So if you imagine this is kind of a top-down view, and this is the top of the box, and here's me, that my line of vision, my face, has to be perfectly facing this side of the object. If I turn and I'm looking at the object over here, the corner of my eye, or looking at the corner of another object, you can kind of envision that the object would instead look like this, where I still have perfect verticals, but my horizontals have begun to tilt as that object skews out in space. So, one-point perspective only works when I'm perfectly coplanar, when my vision is perfectly perpendicular to the objects in my scene. So, that's one limitation. Obviously, that'd be a little useless if that was the only thing that perspective can do. So people also came up with systems to draw objects like this. But that gets a little more complicated. So let's begin trying to draw an object like that. So again, I'm going to start with my horizontal. And let's begin with that box I just drew. So obviously, I can't just put my vanishing point right in the center of my page and connect my lines up to it, because it doesn't line up with anything. It doesn't work anymore. It doesn't make the box, feel like it's sitting in space. So I need to figure out something else. But I still know that all parallel lines recede to the same point. And so they don't seem to be receding to this point anymore. But I know, for example, that these 3 lines are parallel. So they must recede to the same point on my horizon line. And I also know that these 3 lines are parallel to each other. And so they must recede somewhere on the horizon. And so essentially what's happened is that I haven't broken the perspectival system, but I've had to add another point. So now instead of this central point, we're going to have 2 vanishing points that sit on either side of our object. And this is a 2-point perspective system. So let's begin drawing our object. So I'm going to start with a vertical line. And what I'm going to do to begin is I'm going to connect the top and the bottom of my vertical line to each of my vanishing points. And so I've created a kind of chevron shape that we could also see of as think of as maybe like an L-shaped wall we're seeing into space. Now, just the same way that I used a horizontal to add a back onto my box in 1-point perspective, I can add verticals onto this wall that will sort of begin to give some dimensionality to it. And I'm going to take the tops of these lines and send them over to my points. And you can see that now I have a box that appears to exist in space. And just the same as with 1-point perspective, any object that is parallel to this object, that's square with it in space, is going to share the same 2 vanishing points. So, buildings on a city block, or things that are in line on a table. Basically anything that is in line with each other is going to share these same vanishing points. So, see? And actually, for anyone who's curious, the homework for today was to, just the same way that I had you draw a scene with 9 boxes in 1-point perspective, I want you to draw 9 boxes in 2-point perspective. So we're going to have 1 line here, 1 line here, 1 line here, there, and to build boxes out of each of these vertical lines. There are going to be, for example, scenes where I only have to connect. There we go. Sorry, my shift key was stuck down. I only have to connect the top and the bottom. I don't have to go through and continue to draw the other lines because those would be obscured by my object in the end. But anyway, that was the homework. But 2-point perspective, while more useful, also has some limitations that make it not always applicable. The first is that, especially in 2-point perspective, there are going to be lots of situations where our vanishing points are not on our page, which means that we can't physically take, for example, a ruler and draw a line from a point to our vanishing point to figure out where that line is going to recede to. A perfect example of this would be, for example, what we drew in class today. So we drew a building. Imagine that my sort of white canvas here is my page, and I've placed my horizon here, and I'm going to really lightly begin sketching, for example, a building out onto my page. These lines are going to touch somewhere, but it's not going to be on my page. It's going to be somewhere off to the right. Same thing over here. These are going to touch somewhere here, but it's going to be somewhere off to the right. If I wanted to include those vanishing points on my page, so again, imagine that my page is kind of the dimensions I'm working with here. Depending on how large the object is, depending on where I want to crop my page, I might end up needing to make that object very small on my page in order to make the angles appear correct, which may not be, so this is sort of where my page was before, which may not be something that I'm willing to do. And it may not be possible to do if I ever want to make a drawing more than, 3 square inches. So, and major limitation is that the vanishing points may not be on our page. Other limitations include situations in which I have too many objects going at too many angles. So, for example, with our objects before, we started with kind of 2 arbitrary points and a vertical line, and we built our box off of that. And I mentioned that I can make another box using these same points. But using the same 2 vanishing points implies that these boxes are parallel with each other, implies that they are square with each other, that they are right angles to each other. Again, like buildings on a block, they are on a grid. If a box that I want to make, for example, skews out of line with that, so it's at a slightly different kind of angle than the other 2. So these lines no longer meet at these 2 points. This will meet somewhere off to the side, this will meet much further out to the right. These lines will still converge at some point off to the left. These lines will still converge at some point off to the right, but we have additional vanishing points. A lot of times we'll have a scene that's so complicated or has so many boxes, so many different directions, that it may not be worth our time to find the actual vanishing points for every object, even if they are on our page, because it's going to be, maybe 20 vanishing points on a page. So why are we talking about all this? There are a few reasons. The primary reason is that the conclusion, the irrefutable conclusion of linear perspective is that if I have a rectilinear object the orthogonals that go back into space must converge. They must touch at some point. They can't be parallel to each other so that they would never ever touch, and they certainly can't open up towards the back. I can't have a box like this. Neither of these are possibilities. It has to be this. So even if we don't actually have our horizon line on the page, even if we don't actually have our vanishing point on the page, it's very useful. Same thing when we're drawing in two-point perspective. It's very useful to keep in mind the idea that these lines are going to have to meet at a point at our eye level somewhere, sometime. It's a very good way to kind of catch ourselves from making simple mistakes, from making boxes that kind of, open up towards the back in ways that, don't quite seem to make actual logical sense. So that's really the key point of linear perspective for right now. Next lecture, we're going to get into drawing ellipses, which is a circle turned back into space, and linear perspective is incredibly useful for that because we can kind of set an ellipse into a rectangle or a box, and then use that box to help us draw, for example, a cylinder. But we will get into all that then. I realize now, I don't think we can go back and re-record this whole thing, but I forgot one of the limitations of perspective that I mentioned in class today that I forgot to mention now, so I'm just going to squeeze it in here real quick, which is that linear perspective only works with a fixed vantage point. That means that I cannot move my head, I cannot move my eyes. I have to have my eyes fixed at a point in space. In one-point perspective, the point that I'm fixed in space is going to be the vanishing point. Objects will always appear to vanish to the point in space that I am looking, which is going to be the center of the page because it's my center of vision. Obviously, you can't center your vision on somewhere other than the center of your vision. But if I turn my eyes to the side or I turn my head to the side, suddenly this all falls apart. The same thing is true in two-point perspective. So the end result of this is that I can't draw any scene that would require me to have turned my head in order to see all of it. So as a quick example, let's say that here's my eye level, and I'm going to make a drawing on my page, and on my page I'm looking at a box in two-point perspective that's kind of sitting in front of me like this. And I decide that I'm going to also try and draw, maybe like a pipe, some kind of control panel, maybe like an electrical box that's attached to the ceiling. And I tape some extra pages onto mine to make it all the way up there, and I begin to draw this box that's all the way up here. And well, that doesn't look right. And it's because I would have had to have moved my head to look at that. And as soon as you get beyond the sort of cone of vision that we can see with our head in one fixed space, everything gets all wonky. It really only works from one vantage point. The same thing's going to happen if I turn my head left and right. If I, for example, wanted to draw, a long hallway, I might see that, okay, the space is sort of extending out here, and as I turn my head, it appears to flatten out, and that would converge again to the other side. I kind of get this fisheye lens effect because I've turned my head while I've been working. It's kind of, the same thing as if you take a panorama with your phone. So our head has to remain stationary if we want to stay inside of true linear perspective. So again, sorry that was kind of out of place right at the end there. The main takeaway, again, is understanding that there is a line in a scene that represents my eye level, and that objects above it I can see the bottom of, objects below it I can see the top of, and so on and so forth with the left and the right. And that in a scene made of rectilinear objects, all parallel lines have to meet eventually at the same point, and that point is going to be on my eye level, on my horizon line. That's the real takeaway. The vanishing points might not be on the page, the horizon line might not be in the page, but they have to converge, and they have to move as if they're going to converge eventually. So I know that was a lot to take in. Hopefully this is helpful. If you're still confused, we're going to be covering linear perspective for a decent chunk of time. Especially once we get into using it to draw ellipses and spheres and things like that, it becomes incredibly useful. And in fact, it becomes almost essential if we want to invent any forms. Having some kind of linear perspective based schema that we can use to create imaginary forms is incredibly useful. So we're going to be talking about that. Please let me know if you have any questions. And again, I hope this helped. I will see you in class.